Hi everyone to our special time seminar. Today, Akihiro Munemasa is going to tell us about Abelian covers of association schemes with application to SIC-POVM.
Yeah, thank you very much for giving opportunity to give this talk. Yeah, so this is a kind of a makeup talk for the conference last month, which I missed because I got COVID-19. And I was supposed to give a talk for the Chris Godsil birthday conference, but unfortunately I had to cancel it. So this is basically the talk I wanted to give there. But for I suppose there are no one here. So the first half of the talk was given in a conference in Japan 3 months ago, but the second half is new. But I suppose nobody participated in the first half, so I will cover all of them. Now, so this is based on joint work with Jesse Lansdown. He's now in the University of Canterbury, New Zealand. So the topic is to construct covers of association scheme and which generalize covers of complete graph, for example. And I discovered its connection to the complex equiangular line that's also called symmetric informationally complete positive operator value measure. It's too long, so people usually say SIC-POVM, I suppose. Okay. So the idea is to enlarge graph by adding extra vertex. Yeah. Or you start with a given graph and place that graph in the neighborhood of a vertex and construct a larger graph. This may be called the graph extension, and that goes back to the work of Ernie Schultz in '72. So in terms of the metrics, so let A1 be the adjacency matrix of a given graph delta, and A2 the adjacency matrix of the complement. So the picture shows that I add a new vertex and call it infinity, and new vertex infinity is joined to every other vertex of which is just all vertices of the graph delta. I put a plus here because I'm going to make a copy of this configuration, but to describe this part, it's enough to consider this adjacency matrix A1 tilde, where I have an extra row and column corresponding to the new vertex infinity. Yeah, so I make another copy, but the same graph delta. Just to distinguish with the first one, I put minus, and then I join two vertices, one from delta plus and the other from delta minus, call them x and y, and they are joined precisely when the corresponding vertices in delta are non-adjacent. So this is conveniently described in terms of adjacency matrix, where this off-diagonal block represent the non-edged A2 that complement. But I need also this extra row and column that the infinities are not joined. So this construction can be conveniently described in terms of this 2x2 block matrix. So it consists of two steps. The first step is to add extra row and column, and then make another block matrix with 0 row column, and then combine or arrange them into 2 by 2 block matrix. And this construction is also known as the construction of the Taylor graph. So if you start with a strongly irregular graph, strongly irregular graph is described in terms of parameter vk lambda mu. The v is the number of vertices, and k is the valency. And any adjacent vertices have lambda neighbors, lambda common neighbors, and non-adjacent vertices have mu common neighbors. So these are the meaning of the parameter vk lambda mu. I hope everyone is familiar with strong irregular graph. And the special family of strong irregular graph allows one to construct a nice graph of diameter 3. So if you have a strong irregular graph with the extra condition that k is equal to 2 mu, then that graph extension construction that I described in the previous page gives distance regular antipodal 2 cover of the complete graph k b plus 1. So v was the number of vertices of the original graph, and because I added infinity, so there are v plus 1 vertices on the half, and then I made 2 copy, so that results in 2 cover of the complete graph. So this construction is described fully in the book by Brouwer, Cohen, Neumeyer. It's in a very early part. If you haven't studied this, I recommend reading this book. This book is very difficult to read through, but it appears in the very beginning. It's section 1.5, so you don't have to read very much. So we call graph arising in this theorem a Taylor graph. So the whole point of this talk is to generalize this construction of Taylor graph from certain nice graph like strong irregular graph. Okay, so the first analog, or not quite generalization, but the analog is to replace this strong irregular graph by a digraph. So digraph is means that just a direct graph, but here I'm concerned with the doubly regular tournament. So if you know association scheme, this is nothing but the non-symmetric association scheme of class 2. So doubly regular tournament has 2k plus 1 vertices, and k is odd, and it is k regular. And adjacency matrix satisfies this condition. And the complement has adjacency matrix A2, but the complement is nothing but the reversal of orientation, so it is the transpose of A1. So whenever the adjacency matrix A1 satisfies this, the digraph is called the doubly regular tournament. Now, one could do something similar to the Taylor graph construction. So if delta is a doubly regular tournament, then I add 1 extra row and column. But here, I want to make a digraph, so I can't have 1 here, but instead 0. So that A1 tilde doesn't have a undirected dead. And instead I have 1 here for the complement. Well, not exactly the complement. Here I don't mean to construct the graph, but rather a 3-class association scheme. Well, that last relation is a kind of trivial one, just identity. So this is just like a 2 cover appearing in the Taylor graph. And this part of the construction is quite similar to the Taylor graph. And it turns out that if you start with doubly regular Tolman, this gives a 3-class association scheme. So I wrote this paper quite recently, but in fact, this is essentially due to Babai and Cameron, published in 2000. They wanted to introduce, or they wanted to study the analog of 2 graphs, or switching class of graphs in the directed setting. If you are familiar with 2 graph and switching class, then you know that they are essentially same object as Taylor graph. So it's not surprising that you get directed analog of Taylor graph if you consider the directed analog of 2 graph or switching class. Okay. Now, next, let me discuss antipodal covers of complete graphs. So let n be a positive integer at least 3, and r is also a positive integer at least 2. I need to consider r cover. A graph gamma is called antipodal r cover of the complete graph Kn if the set of vertices admits an equitable partition into n co-cliques of size r. So this graph gamma has n times r vertices. And the set of vertices is partitioned into n co-cliques of size r. So the edges appear only between co-cliques, and any pair of these co-cliques induce a matching. So if you quotient by identifying vertices in the co-clique, then you get a complete graph on n vertices because there are n co-cliques. So Taylor graphs are a special case of this antipodal cover. In particular, it is 2 cover. So the first goal is to construct a distance regular antipodal 2 to the power t cover of complete graph by using an amorphic pseudocyclic association scheme of 2 to the power t classes on endpoints. Okay. For example, let me give first a smallest non-trivial example. Maybe some of you are not familiar with what amorphic pseudocyclic association schemes are. So here is an example. Consider the Cayley graph. In fact, that may also be called generalized Paley graph. It is not quite the Paley graph, but it is defined in terms of quartic residue, not quadratic residue. So if you take zeta to be the primitive element of the finite field of 49 elements and consider subgroups of 4th power, and there are 4 cosets, and that gives 4 edge disjoint Cayley graphs. And this collection defines amorphic pseudocyclic association scheme. So here n is 49, so n plus 1 is 50, and t, so this 2 to the power t is this one. There are 4 classes, 4 graphs that partition the set of edges of the complete graph. So it is a 4 cover of Kn plus 1, that's K50. So this is the typical example of our construction. Distance regular antipodal R cover, not just the antipodal R cover of complete graph, but if you require distance regular then it is described in terms of a quotient matrix of the equitable partition. Usually it is written in terms of intersection array, but here I wrote in terms of intersection matrix. I will explain the meaning of these parameters in the next slide. So diameter 3, here diameter is 3, so distance 3 is an equivalence relation, and equivalence classes form an equitable partition into co-cliques of size R. And any pair of these co-cliques induce a matching. And that was a definition of antipodal R cover, but there are extra conditions needed to ensure distance regularity. That is shown in this picture. So if you fix a vertex here, and then n-1 is the valency of the vertex, and C2 is the number of common neighbor of two vertices at distance 2. And R-1C2 is the number of edges going from the first layer to the second layer, and similarly from the third to fourth, second to third layer there is only one, and from the last layer you have n-1 edges coming back. And this last part is a co-clique. Yeah, this kind of graphs are studied by Godsil and Hensel in 1992. They introduced how this cover can be constructed from abelian group, not necessarily abelian, but the large example comes from abelian group. So they defined the symmetric arc function. So symmetric arc function is a function defined on the set of pairs xy with x and y distinct, coming from a same set capital X, and taking values in a finite abelian group, satisfying the condition that if you switch first and second coordinates, then the value becomes the inverse. If you have this kind of symmetry function, if you have this kind of function, then one can construct the antipodal R cover of complete graph on n vertices, complete antipodal R cover of complete graph of n vertices, where n is the size of the set X and R is the order of the group G. So it's easy to describe. The set of vertices is just the direct product X times G, and two vertices xg and yh are adjacent whenever the G multiplied by the value of f at xy is equal to h. So in this way, antipodal R cover of a complete graph can be constructed, and then one can state in terms of f when the resulting cover is distance regular. Now, the first goal is to take G to be elementary abelian group, and take X to be a set consisting of a distinguished vertex infinity, and together with another, the rest Y, where Y carries an amorphic pseudocyclic association scheme. So X itself is not a amorphic pseudocyclic association scheme, but X is obtained by adding extra vertex to a scheme. This is just like the construction of the Taylor graph, where you add infinity to a strongly irregular graph, and then make a copy. So here, making a copy is replaced by taking the direct product with a finite group G. So not only 2 cover, but R cover, where R is a power of 2. So let me briefly explain what the amorphic pseudocyclic association schemes. I don't give the precise definition because some conditions are in fact unnecessary due to the work of Van Dam. So roughly speaking, the amorphic pseudocyclic association scheme is a collection of edge disjoint strongly regular graph with the same parameters. So there are 4 parameters. The first one is the number of vertices V, or rather, this is the size of the set Y. And next is the valency. The next is the parameter lambda. That's the number of common neighbors of 2 adjacent vertices. And then finally, this is mu, which is the number of common neighbors vertices at distance 2. So I assume that the edges of a complete graph on Y is partitioned into R strongly regular graph having the same parameters described here. And then together with the trivial relation R0, we say that this collection of partition of the direct product of Y and Y is called amorphic pseudocyclic association scheme, provided the linear span of the adjacency matrices is closed under multiplication, and the multiplication is commutative. And also there are some other condition, but in fact, Van Dam showed that this is already enough to ensure that the original definition of amorphic pseudocyclic association scheme is satisfied. So such a scheme can be constructed using finite field, just you saw before in the previous slide, like 49 element field. Now, what we proved with Jesse Lansdown recently was the construction of antipodal cover of complete graph using amorphic pseudocyclic association scheme. So we assume that the number of classes of amorphic pseudocyclic scheme is a power of 2, like 4 on 49 vertices, and then fix a bijection between the set of integers from 1 to R to group elements, elementary abelian group of 2 to the power t. 2 to the power t is precisely R, so they have the same number of elements. And then I just do the same construction as I showed you in the construction of Taylor graph. I take up one particular relation. I have to warn you that this particular relation is not the trivial relation, but rather one non-trivial relation. This bijection is defined on the set of positive integer, so 0 is excluded. So you may think of this one of the element, one of the non-trivial relation corresponds to the identity of the group, say 0. So for that relation, I add this one vector, row vector and column vector in the first row and first column, and all other relation, yes, I just add 0. So this is how I extend by adding one extra one extra vertex, just like Taylor graph. And then I arrange these matrices into block form, but not this time it is not by 2 by 2 block matrix, but the R by R block matrix. So it is not easy to describe in terms of actual block matrix. So I used Kronecker product instead. Well, to describe Kronecker product, I use a regular permutation representation of the group. So every finite group can be realized as a permutation group on the group itself. So so this is a group of order R. So you can convert group elements into R by R permutation matrix acting on the group itself. So this is known as the regular representation. So instead of describing the result by block matrix, I use Kronecker product. For example, if T is 1, and this is just a group of order 2, so the image is just 2 by 2 matrix. So for example, this is like 0, 1, 1, 0. So this Kronecker product gives exactly the 2 by 2 block matrix. In general, it's difficult to describe in terms of matrix, so I have to use a more compact notation that is Kronecker product. But the idea is the same, and the result is also the same, that this B is the adjacency matrix of a distance regular antipodal R cover of the complete graph on this many vertices, because I started with Y, and I add one extra row and column. That's the first step. And the second step is take the R cover. Okay. So this was the first goal. Okay, so yeah, exactly half an hour. Yeah, I'm not sure this construction is interesting enough, because our construction results in graphs equivalent to certain group divisible designs. It's well known that group divisible design gives rise to covers of complete graphs. So also there's a concept called divisible design graph, and our graph belongs to this family. Now, in this expression, I used Kronecker product, but there's an alternative way to describe the adjacency matrix, and that was actually used by Godsil and Hensel, and more recently by Coutinho and Godsil, Shirazi and Zhan. They use the slightly different language, but essentially the description is the matrix algebra over the group algebra of the Abelian group. Because taking the Kronecker product has the effect of inserting inserting this matrix into the entry of this 0, 1 matrix. That has effect of replacing entry of this matrix by this permutation representation, but this regular representation can be identified with the elements in the group algebra. So in that sense, one can view that this adjacency matrix B lives in the matrix algebra over the group algebra. Well, it has a nice feature that the eigenvalues of the matrix B can be computed using this structure. You will see the computation of the eigenvalue in the different setting. Now, this is the same theorem again, but in the second half of this talk, I will present a modification of this theorem. The modification is done for this red part. So I change this assumption that I use different kind of association scheme, not amorphic pseudocyclic association scheme. And I also change this group, not the elementary abelian group, but arbitrary finite group. And this part is saying the arbitrary finite group has the identity element, or maybe not appropriate to denote by 0, but it's better to denote by 1. And also the arbitrary finite group has a regular representation. So this part is essentially the same. But the main difference is the conclusion. I do not get distance regular antipodal R cover, but something different. So that was, if you remember the title of my talk, then you will see what you get, what I'm going to get. This is the cover of association scheme. So the result is an association scheme. So of course, distance regular graph is also regarded as an association scheme, but in the modification, the result is not necessarily distance regular, even not necessarily symmetric association scheme. So instead of amorphic pseudocyclic association scheme, I start with an arbitrary commutative association scheme with R classes, adjacent symmetries is A0 to AR. And as I said, G is a finite abelian group of order R. So it's important that this order R coincides with the number of classes of association schemes so that I can construct a bijection between the set of integers from 1 to R to the group G. But here I need to assume one extra condition that this bijection preserves or is consistent with transposition of the relation and the inversion of the group element. And this is automatically true if you have a symmetric association scheme and G is elementary abelian group, because this involution is trivial. But if G is not an elementary abelian group, then inverse may not be the same element. And if association scheme is non-symmetric, then transpose is a different relation. So I assume that these two operations are compatible in this bijection. Now, the next step to add one extra row and column, this part is the same, exactly the same as the construction of the Taylor graph. So I add one extra row and column for the relation corresponding to the identity element. This is, so you might want to call the A1 correspond to the 1 in the group 1 identity in the group G. In that case, I create A1 tilde to be this extra or 1 vector, and all other relation the relation metrics are enlarged by adding 0 row and 0 column. And again, let rho be the regular permutation representation. And in the previous theorem, I constructed only one matrix, B, that was supposed to be the adjacent symmetric of a distance regular graph. Here, I mean to construct a family of adjacent symmetries. So AI tilde is a 0-1 matrix, and this is a permutation matrix. So its Kronecker product is also a 0-1 matrix. And it's easy to see that they have disjoint support. And also another family of 0-1 matrices I call C of G. In terms of Kronecker product, I have identity times this row of G. So in total, there are 2 times R. R is the order of group G, 0, 1 matrices, and they partition the O1 matrix. I mean, these are 0, 1 matrix whose sum is equal to J. So it's not. Then I want them to form the set of adjacency matrices of association scheme. Of course, I haven't assumed anything significant, so this conclusion is not true in general. So I need to assume something. So the condition will be described in the next slide. So this is the construction, and it generalizes the previous one for amorphic pseudocyclic scheme with elementary abelian group. That is the condition comes from for that case is that we need to assume that the scheme is amorphic pseudocyclic for G to be elementary abelian. In this case, G is of not necessarily abelian, not necessarily elementary abelian, and then I need to assume some condition on the association scheme. Okay, to describe this, I want to simplify the notation first, because I assume the existence of a bijection between the set of non-trivial relation with group elements of G. So I might as well describe the original association scheme in this form. So the set of relations are indexed by the group G, except the trivial relation with 0 is not the identity element of the group G, but there's something different, not an element of G. R0 is the trivial diagonal relation. And R sub G, where G runs through elements of capital G, or non-trivial relation. And it is assumed that this is a commutative association scheme, and the bijection I mentioned in the previous slide requires that the transpose of the adjacency matrix is the adjacency matrix indexed by the inverse of the element. Okay, and then the construction says that the B sub G, the new large adjacency matrix, is defined in this way. So this enlarged adjacency matrix times Kronecker product of with the regular representation, and this tilde construction is just adding extra row and column, where if H is the relation indexed by the identity element. Okay. So in order for the conclusion to be true, I need to assume one of the two equivalent conditions. So here is the lemma which described the necessary hypothesis in order to get that this set of the set of adjacency matrices form an association scheme. Well, certainly, if they form association scheme, then the square of B1 here 1 is the identity element of the group G, and square in terms of the matrix multiplication. This must belong to the linear span, because that's part of the axiom of association scheme. It turns out that this is already enough to ensure that every product of adjacency matrices belong to the linear span. Now, this condition, the B1 square, can be computed by its definition of B1, and it amounts to this third condition, that if you compute AG transpose time AGH and take the sum over G, and then it is expanded as a linear combination of these adjacent symmetries with coefficient Kg, where Kg is the valency of the relation A sub G or R sub G, and time plus this extra term, which appears only when H is identity. So the last condition can be expressed easily in terms of intersection numbers, because this can be expanded into linear combination of adjacent symmetrics with coefficients being intersection number of the original disassociation scheme. So one could also write down or rewrite this condition in terms of eigenvalue of the association scheme. If you multiply both sides by primitive idempotent, then it becomes just an identity in scalars or eigenvalues. And resulting association scheme has two times order of G minus 1 classes. Well, if G has order R, then there are two R relations, including the trivial relation, so the two R minus 1 classes. And C1 is the identity. C1, in general, CG is identity Kronecker product, the regular representation of G. So C1 is identity times identity. So C1 is identity. So this is the kind of A0 or the trivial relation. And it is symmetric if and only if G is elementary abelian group, because we don't have to worry about BG, but the CG is already non-symmetric if G is not involution. So so the result has many classes depending on the order of group, and typically if G is elementary order abelian group of order 2 to the power t, then there are 2 to the power t minus 1 classes. But it admits a fusion. For example, it gives a distance regular antipodal R cover. So it has a fusion of class 3 when G is elementary abelian. So let me describe that fusion. So the fusion is described in this manner. The construction gives a large number of adjacent symmetries BG and CG indexed by group element G, but there is one particular adjacent symmetrix B1. Here B1, this 1 is the identity element of the group G, but 2 is not the identity element of the group G, and so it's a little bit, it's by a clash of notation to this B sub G. The subscript is supposed to be element of group G, but except 2 and 3, B2 is defined by this formula. B1 is defined already in terms of group element, identity, and in some sense the B2 is almost like a complement. B3 is really the kind of equivalence relation or antipodality relation. And this is how the resulting scheme of many classes can be fused to give a antipodal R cover of a distance regular graph, distance regular antipodal R cover of a complete graph. Okay, now next, I want to give an interesting example by taking G to be a cyclic group of order 4. This is not elementary abelian, so I need the non-symmetric association scheme of class 4. So I need to start with the association scheme of class 4, and the 4 classes are indexed by the group G of cyclic of order 4. And this group G has 2 non-involution. So there are 2 non-symmetric relations and 2 symmetric relations together with a trivial relation. And the construction says that if this identity is satisfied, then we have a 7-class association scheme. Well, 7 is 8 minus 1, that is 2 times 4 minus 1. That's the number of relations. So the number of adjacent symmetries is BG, CG. So there are 4 elements, 4 BG and 4 CG. One of CG is identity. So there are 7-class association scheme, and it is non-symmetric. Yeah. So, but in order for this to make sense, I need to find an example of association scheme of 4 classes, non-symmetric, satisfying this identity. It turns out there is one. Here is the example of association scheme satisfying this hypothesis. This association scheme has 63 vertices. And this is a non-symmetric because it has imaginary eigenvalue. So these 2 are a pair of non-symmetric, antisymmetric relation, and these 2 are symmetric ones. And one could fuse these 2 non-symmetric relations to make a 3-class symmetric association scheme. And that turns out to be the well-known association scheme called the generalized hexagon of order 2, 2. In fact, the generalized hexagon is a incidence structure of 60 of order 2, 2 is a incidence structure of 63 points and 63 lines, and it gives rise to the bipartite distance regular graph. And this is one of the bipartite halves. It turns out that these 2 bipartite halves are not isomorphics, and one has to take the correct one, and the other one doesn't have this fission. Now, to compute the first eigenmetrics of the resulting association scheme, we first compute the intersection matrices in general. So they recall that intersection matrices are nothing but the matrix representation of the left multiplication of the adjacency matrices expressed in terms of the basis of adjacency matrices. So B is the sequence of matrices, that is, those are the adjacency matrices, and they form a basis of the Bose-Messon algebra. So if you multiply CH from the left to the sequence of bases and write this in terms of linear combination, here is a coefficient, and that's the matrix representation of the left multiplication operator. And also the same for B sub H. And from the definition of CG and BG, it's possible to compute these matrix representation. So the eigenvalues of these adjacency matrices are nothing but the eigenvalues of these intersection matrices, because this matrix representation gives an isomorphism from Bose-Messon algebra to this matrix representation, and these are written in terms of regular representation of the Abelian group. So using the fact that the Abelian group, the regular representation of Abelian group can be diagonalized, it's quite straightforward to find the eigenvalue. This idea appears already in the work of Coutinho, Godsil, Shirazi, and Zhan. And also this method is called the polyphase matrices in the work of Ficus, Jasper, Nixon, Petras, and Watson more recently. So in this manner, the eigenvalue of these intersection matrices can be computed. Here's how we compute because each. Sorry, I should write row h. So these are just maybe I should. These are the regular representation. Did I try use it? Yeah, row h is correct. Yeah, so these diagonal blocks are regular representation. So somehow I use the old notation of mine. So the regular representation can be diagonalized because G is a Abelian group. And diagonal entries are indexed by irreducible characters of the Abelian group. So this is just a diagonal join of diagonal matrices. And this 2x2 matrix is block diagonalized to with 2x2 blocks of this form. So the finding eigenvalue reduces to finding eigenvalue of this 2x2 matrix, and that can be done once you know the valencies of the original association scheme. We know the valency because we know the eigenmatrix. So using this method, it's possible to compute the resulting associations, the eigenmatrix of the resulting association scheme. So I start with this generalized hexagon on 63 vertices and use a cyclic group of order 4. And that construction gives a 7-class association scheme. So the eigenmatrix is 8 by 8. And these are the valencies. And it has several non-symmetric relations. So what is of this use? This is a very remarkable association scheme. Why? Well, if you invert this first eigenmatrix, then you can compute the second eigenmatrix, and you notice that this second eigenmatrix has one particular column with first entry 8. 8 is the multiplicity of the eigenspace. Well, it has this column, but for the sake of the space, I wrote this column vector as a row vector. So 8 on the top, and the other entry of that column given in this way, and the second eigenmatrix indexed by the row. I mean this vector is indexed by the adjacency matrices, so that's why I wrote these 8 adjacency matrices on top. But the entries are actually these. And why is this significant? Well, this implies that this association scheme can be realized as a subset consisting of unit vectors in 8-dimensional complex space, because the multiplicity is 8, invariant under the multiplication by I. That is, there are thin relations. In addition to the trivial relation, there are 3 thin relations, and these 4 thin relations are isomorphic to the cyclic group order 4, that is the cyclic group generated by imaginary unit. So the vectors are invariant under this multiplication. Moreover, the absolute values of inner products are 1 if the vectors are some scalar multiple of the other, and otherwise it is one third. Well, the inner product is obtained by dividing all by 8. That's the dimension. So it's obvious that if you have a vector and multiple by a power of I, then the inner product is just a value in this group. Otherwise, it is always of absolute value 1/3. And how many vectors do we have? Well, we started with the generalized hexagon on 63 vertices and add 1 extra vertex to make it 64. And I made a 4 cover by Kronecker product with the regular representation of group of order 4. So I have 256 vertices. That's the number of points in the association scheme. And there's an equivalence relation defined by this multiplication. And so the 256 is divided into 64 vectors, 64 classes, and these form a SIC-POVM in C8. Well, just in case if you are not familiar with SIC-POVM, here is a definition. So this is a finite set of complex unit vectors in n dimension, and the number of vectors is n squared, and the values of the absolute value of the inner product of distinct vectors is 1 over square root n plus 1. Here in our case, n is 8, so the inner product is 1/3. There's a similar construction. There's another well-known example in complex 3-dimensional space. In this case, if you use 3-class association scheme and cyclic group of order 3, one obtains a 5-class association scheme, and that gives 27 points in 3-dimensional space and consists of 9 vectors up to scalar multiple, and they form SIC-POVM in C3. Okay, fine. This is the final slide. So the data of this association scheme on 256 points representing this SIC-POVM was provided to us by Sho Suda, who together with Alexander Gavrilyuk showed the uniqueness and triple regularity of this association scheme. Yeah, because of the triple regularity, the neighborhood of a point with respect to a relation carries association scheme. So it's natural to expect that the bigger scheme can be constructed from the neighborhood by the Taylor graph-like construction. And this is what we actually did. And it worked. Okay, so that's all for my talk. And thank you very much for your attention. Oh, there is chat.
Thank you so much.
Sorry. Yeah.